this is Junichiro Horikawa, and this is the 14th episode for VEX for algorithmic design. And today's topic is quaternion. The quaternion itself is expressed with four numbers, which is x, y, z, and w. And in Houdini, it is expressed as vector 4. Now, if one say quaternion, most of the time it means the rotational transformation in 3D space, which contains two information. One is the rotational axis and one is the rotational angle. So you can consider that this quaternion contains the information of the rotational axis and the angle, how much it rotates. If you want to know the mathematical equations, how you express this axis and rotational angle with these four numbers, you can express it like this using a trigonometry. First of all, let's define this axis as n and deconstruct this n into a x, y, z value, which is the length in x direction, y direction, and z direction. I'm going to call this nx, ny, and nz, which is the scalar value. Okay, and by doing it, we can express this x, y, z, w with a foreign equations. First of all, a sine phi divided by 2 multiplied by nx, that will be the x value. Sine phi divided by 2, or theta divided by 2, and y sine theta divided by 2, and z, that is the x, y, z value. And the last w value is expressed as cosine theta divided by 2, and that's it. So in those four numbers, it includes the information about the axis, which is this nx, ny, and z, and those theta, the angle value. And this is how you express this information with a quaternion with these four numbers. But when you're using like VEX functions, all these are hidden inside the function, so you don't really need to remember about these equations. Just remember that this quaternion is expressing two values, two main values. One is the axis for the rotation and one is the angle for the rotation. So if you just know the basic idea of this quaternion, that it contains main two information, you'll be able to just use it using the really useful functions provided by VEX in Houdini for a 3D space rotation. So you don't really need to worry about these complex values, complex equations, or complex mathematical process that it's going to that it's doing in order to rotate one vector to another direction. Now, as I have just told you, what I mean by rotation is that you can rotate the vector value from one point to another point using an axis and the rotation angle. Vector can sometimes be the directional value, sometimes can be a positional value. You can rotate both of the values using with this quaternion. And let me show how exactly you can use it inside Houdini with some examples. The first thing first, let's see how you can declare a quaternion. One of the ways is to just use a vector for variable to create a custom quaternion value by yourself. Let's use a attribute wrangle named as vector 4, and I'm gonna change this to detail. Let's say vector 4, and I'm gonna set the name of the variable as val and say set 0, 1, 2, 3. So I have just created a vector 4 value, which is equivalent to a quaternion, and you can manually create this quaternion value by just setting x, y, z, and w by yourself. And if you want to apply it to the attribute value, in this case a detail attribute, you can say the shortest expression to set it to a attribute is called p at, let's say, val is equal to val. Okay. Now let's look at the geometry spreadsheet to see how it looks like. It's pretty similar to what it looks like as a vector. The only difference is that you have a fourth number. Now, and it's pretty easy. I mean, it's pretty straightforward to create a vector 4, but the problem is that from these 4 numbers, it's a bit hard for people to recognize what's the axis information and the angle information from these 4 numbers. As I've told you, the quaternion is mostly used for the rotational transformation, and it includes the axis information together with the rotational angle. But from these numbers, it's a bit hard to estimate what it actually does. So there is another way to create a quaternion value, which is a function called quaternion. And most of the time, when you want to create a rotational transformation, you use this quaternion function. Let's see how we can do that. So I'm going to create another attribute wrangle next to this, and let's set it to detail as well. And let's create a new quaternion value using a function called quaternion, which you can do like this. So vector 4 val is equal to quaternion. So there is a function called quaternion VEX, and using this you can calculate, or you can create this vector 4 value or quaternion value using several parameters. And one of the most used parameters are the angle for the first parameters and the axis for in a vector and as a second parameter. So for the angle, you have to type in the angle in radians, which is in between 0 to 2 pi. So let's create some angle parameters here. Float angle is equal to CHF angle, and let's convert this channel parameter to radians. Consider that the channel rate angle is going to be the degrees, and then I also need some axis values, so I'm going to create the axis, and let's also create the channel for this axis value. And now that I have angle value in radians and axis as a vector, I can type in those two values in a parameter for the quaternion to create a vector 4 value. Now for these, I'm going to set the angle range from 0 to 360 degrees. Okay, and let's change those values randomly. Alright. Now let's also make this axis as a normalized vector, which is always a good idea when you want to use this as an axis or in any other functions related to transformations. Sometimes the size of the vector will affect how the object is going to be transformed. So whenever you want to transform things and you want to use the vector as a guide, then normalizing is a good idea. Okay, now that I have created the vector 4, I can try to see that value by setting it to an attribute called val for the detail. And I'm gonna name this create quaternion. And let's see what kind of values we get in detail. So there's the 4 numbers, and it's a bit hard to see for us what kind of transformation it does, what kind of rotation it does, but those 4 numbers actually determines how the object should be rotated in what axis and what angle, using the equations that I show you in the introduction. Now that we have this quaternion value, let's try to use this to actually rotate some vector value. I'm going to create a new point. And I am going to apply some vector to this point. Now currently the point doesn't have any normal value, so let's apply some normal attribute to this one using attribute create. I'm going to name this as n, capital N, and type as a vector value. And let's set the default vector value as a y or x direction equal to 1. Okay, and let's try to show this normalized vector, normal vector, by clicking this button. Then if you see this blue line, it's okay. You can also check it by going into the point attribute in a geometry spreadsheet. If you see this n attribute, then you're good to go. Now what I want to do now is to create a quaternion in order to rotate this n value or n vector. So let's do that by using point wrangle connected to this one, and let's say rotate vector. And first thing first, we need to create a quaternion like we just did. So first we need an angle. Let's convert this into radians as well. And E-axis, let's also have this as a channel. Okay, and let's calculate the quaternion. Vector 4, and in this case I'm going to name it as quat, is equal to quaternion, and the first parameter was the angle, so ang. The second parameter was the axis, so axis. Now in order to use this vector 4 value or quaternion value in order to rotate this vector, there is just a function to do that, and that is called qRotate, meaning it uses a quaternion to rotate a vector, and the output you get is the rotated vector. And the parameter for in order to use this one is the first input is going to be the quaternion that you're going to use it as a rotational transform information. And then the second parameter will be the vector that you want to rotate. So in this case, the first parameter will be quaternion, and then the second parameter will be the one that I want to rotate, which is at n, a blue line of this one. Okay, and as an update, I'm going to replace the normal direction like this. Okay, now let's promote these vector value and the axis value and the angle. And let's set the range for the angle from 0 to 360 degrees. And also let's normalize this axis value. First I'm going to set the axis to some random values like these, and then try to rotate this by increasing the angle. And you see that the angle, this normalized vector, normal vector on a point, is starting to rotate with this angle numbers. And it might be better to see why it's rotating like this by showing the axis vector as well. So let's right click this marker button or visualization button here and click plus marker, and let's add a axis vector to visualize this invisible axis vector on a point. Okay, and let's set it to vector, and let's assume there's an axis attribute on a point. Color is yellow. Okay, now I don't have this axis being applied to the point yet, so let's create a attribute for the point called axis and store this axis value like this. Now you can see that this yellow line is the axis, the rotational axis, and using this as an axis by changing this angle value, the blue line is rotating around it. You see it like this from 0 to 360 degrees. And if you change this axis to some other different direction, the new rotated angle will be rotational transformation will be created using this new yellow direction as an axis like this. So this is how you can use Quaternion in order to rotate a vector value with an axis and the angle value. Now let me show you some simple example how you can actually use it. First of all, I'm going to show you how you can rotate the object with the mesh object with several points using this Quaternion to rotate. Okay, so first of all, I'm going to create a sphere geometry, and I'm going to try to rotate this sphere geometry, rotating whole points all together to make it look like the whole object is rotating with an axis and the angle. Right? And I'm going to make this as a polygon to have points. Okay, I'm going to show the edges as well. I'm also going to convert this into a line so that it will be easy to see inside how it's being transformed. Right. Now next thing I would like to do is to create a axis. Now I'm going to make a axis a bit more visualized by creating a line, and I'm going to set this line as an axis for the rotation. The length doesn't really matter, so I'm going to set it to 2, and I'm going to change this angle for the line by using this marker here, so that I can interactively change this axis, this line angle, and I'm going to use this line as an axis to rotate this object. Now to do that, I'm going to use a point wrangle again, and I'm going to use this point wrangle to access all the points on a sphere, and for each of the point I'm going to calculate the transformation, the rotation transformation, using the same axis with the same angle, so that all the object will be transformed in the same manner. Okay, so I'm going to connect this geometry to convert it to line geometry into a point wrangle, and as a guide I'm going to use this as an axis. I'm going to connect this to a second input, and let's name this rotate object. Okay, now first of all, I would like to retrieve the end point of the line, which is here, and I know that the center point, the first point of this line is at the center 0, 0, 0. So by just retrieving this end point and normalize it, you'll be able to get the axis value. So let's do that first. Vector a pass equal to point from the second input P on the second point. Since there are 2 points on the line And when you say 1, that means that's the second point, which is the end point of this line. And after I get it, I can make it as an axis. Let's create an axis vector by normalizing what I have get as a position. Right. So that will be the axis value, this line. Now I would like to create an angle parameter as well. So just like I did last time, first of all, I'm going to create a channel called ang and convert it into radians. Like this. And create a quaternion for the rotation using quaternion function. Ang axis. Okay, and let's set the angles range from 0 to 360 degrees. Right. Now that we have quaternion, we can use this to transform this whole object, and which is pretty easy to do. You just need to access each of the point, and since you're in the point wrangle, you can just do it like this. P is Q rotate using quaternion that I've just created, and rotate this point, every point. And as a result, you'll be rotating the object using this line as an axis from 0 to 360 degrees. And if you change the angle for this line to somewhere random, then the rotational direction will change, and you can create more customized rotation like this pretty easily. So in most of the cases, it makes a lot of sense to use quaternion functions to create a vector 4 value for the rotation, and qrotate to actually use it to rotate the object. This is kind of the most basic set when you are going to use a quaternion in Houdini. And actually there's another way to rotate the object using different method, which is to use matrix, but I'm going to talk about it in different videos. In these sessions, I'm just going to talk about how you can use quaternion for the rotational transformation. And there are some specific benefits using quaternion over matrix for the rotation, so I'm going to tell you about this later. Now let's merge these geometry and axis line together to see the whole setup as one. Okay, now let's try another example. Which is going to be pretty simple as well, but in this case I'm going to try to vary the angle value for multiple objects. So I'm going to try to control multiple points altogether, but using different angle value, and see what kind of effect we get. Right. Let's try to create a line on a x direction. So I'm going to set the direction as 1, 0, 0, like this. And let's also set the number of points to 100 so that we can have 100 points like this. And I'm going to access each of the point and apply a different angle to do a different rotation. Okay, so let's create point angle. Let's name this rotate points. And first of all, I'm going to create a axis, which I'm going to make it pretty simple. I'm just going to make the axis as y direction, which in this case a upper direction perpendicular to this line. And for the angle, I'm going to create the angle based on the number of this point. which you can check it by clicking this spot point here. So each of the point has this ID value from 0 to 99 in this case. So I'm going to create an angle based on those numbers. So you can access that numbers by accessing to ptnum at ptnum. I'm going to multiply this by some channel value, which is going to be the step angle. Also use radians to convert from degrees to radians. Radians. Okay. Now let's promote the angle and let's set the range from 0 to, in this case, 180 degrees. Alright. Now let's create a quaternion with those two information. Vector for quat is equal to quaternion. The first value was angle, so ang, and the second value was axis. Now let's see if I do the rotational transformation for each point, what would happen. At P is equal to Q rotate, and quat with current point. Okay, let's hide those information and let's increase the angle value, and you see this kind of spiral curve has been created. That is because for each point, the first point was rotated 0, so it stays at 0 positions. And for the second point, it used 4.6, and the second point it used 4.6 multiplied by 2, so you have a bit more larger angle value to rotate, and which continues with a multiply numbers, so angle will increment by 4.6 in this case to create, in the final shape it's going to be something like a spiral shape. So this could be considered as one of the most quickest way to create a spiral shape, like this, right? Which can be also considered as a basic of the rotation using this quaternion. Now in some cases you might want to rotate the object not with a angle with the axis, but using 3 different angle value for x-axis, y-axis, and z-axis, which is currently used inside a transform node. For example, let's say if I want to rotate this box, and if you use a node like transform, you see that there's a section for rotation here, x, y, and z. So this one uses the x, y, z value, which is in degrees, to rotate the object in different axes, like this. And sometimes you might want to rotate the object in this way, and there's just a way to do that in Houdini, in VEX as well, by converting this Euler angle, so-called Euler angle, into a quaternion. Now the important thing about this is that the rotational order matters. Like in this case, it is rotated, first rotating using x-axis, and then rotating y-axis, then rotating in z-axis. Now you can actually change those orders, in this case in transform node, by changing these order for the rotation. If I set like this, in this case x goes first, z goes next, and y goes next, and so on. So as you can see, if you change the order of the rotation, then the final rotational look or the final transformation outlook looks different. So the order of the rotation, if you want to use those 3 axis based Euler angle to rotate, then the order is pretty important. So remember this. And let's see how we can use the same rotation in VEX by converting from Euler to Quaternion. First of all, I'm going to create a add node to create a single point, like this. And I'm going to, like I did last time, I'm going to create an attribute using attribute create to create a normal direction. So let's name this as n, and let's have x direction as a base value for the normal, like this. Okay, now let's try to create some rotational value using xyz xyz axis based angle, Euler angle, which is in between 0 to 360 degrees or 0 to 2 pi. Okay, so to do that, I'm going to first create a point wrangle, and let's name this Euler to Quaternion. Now, first of all, I'm going to create a vector of values which contains 3 rotational values. So I'm going to say angles, CHV angles. So you have x, y, and z value, and for all these I'm going to use the degree value to actually rotate the value, right? So since this is all in degrees, I need to convert it into radians again in order to convert from Euler to a Quaternion in VEX. In expressions, you could use degrees like this from 0 to 360 degrees, but if you're using a transformation in VEX, then all of those angles have to be expressed in radians. Now fortunately, when you have an angle with the vector value and all these are expressed in degrees, you can just use a same radians function to return a value as a vector, converting all those x, y, and z from degrees to radians. So it's pretty convenient. Now that we have an angle, next things we want to do is to actually convert this Euler angle value into a Quaternion for the rotation. To do that, we need to use a function called Euler to Quaternion, and you have to specify 2 parameters. One is the rotation vector, which I've just created for x, y, and z axis, and the second parameter is the order, in what order you want to calculate the rotation, if you want to start from x, y, z, or if you want to do for the x, z, y, and so on. And you need to check the constant value for this parameter. So let's check where we can get this information for the order. So first of all, I'm going to say angles, and for the second parameter I'm gonna keep it as empty, and let's go to the documentation page to see where we can find information. So I've come to this VEX functions page, and let's search for Euler to Quaternion. Okay, and if you look at it, it says creates a vector for representing a Quaternion from a vector representing Euler rotations in x, y, and z. And it says the second parameter, specify the rotation order with the order integer, use the constant defined in VEX, include math, for example x form xyz. So it seems like there is an information for the constant value written inside this file. So let's check this file in your Houdini to see what those values are, what the options for these constant values are. Right. So let's first thing I'm going to do is to copy this one, or maybe copy this directory here and go back to Houdini. Now next thing I'd like to do is to open up the HScript textboard to check what's the exact path for this path. Enter. Now it gives you a path where it is saved. So I'm using a Mac version of Houdini currently, so this is the path where the math.h is saved. If you try to show this on Windows or Linux, you should be able to see a different kind of path. So I'm going to copy this one and see the folder inside here. Now this is the folder which has been specified, and let's see where is the math. Okay, here it is. So let's try to open this using some text editor. Okay, so if you open this, you see a bunch of constant value, and you'll be able to see what you want to use, which is these values. Define x form xyz, xdy, so on. So these are the constant value which can be used to specify the rotation order. So when you use either x form xyz or 0, it means that the rotation order starts from x and then goes to y and z, and there is until 5, so meaning there's in total 6 rotational orders. I'm just gonna keep it as 0 or x form xyz, so I'm going to copy this one, go back here, and for the second parameter I'm going to paste x form xyz, and that should just work. Now this will create a Quaternion vector 4, so let's create a variable called quat, and let's try to see this inside an attribute named as quat. In this case this was point wrangle, so if you go to the point and if you see this quat, currently it says 0001 because there is no rotation applied yet. Let's say if I want to rotate this x axis with the 30 degrees, then this will create a new Quaternion rotation like this. Alright, now let's keep it to 0 for now, and now that we have Quaternion created using those 3 Euler angles, we can then use the same qRotate to actually rotate the vector, in this case a normal vector. So at n is equal to qRotate Quaternion at n, like this. Okay, I think I am missing something. Okay, I realized that when I created the normal vector n, I didn't change it to vector, so let's change this to vector. Now let's go back and let's see. Okay, now it's not rotating anything yet because all the angle is 0, so let's try to rotate this vector using y-axis, which in this case this one. So if I increase this value by 10, you can see that it is rotating in y-axis, using y-axis. If I add the x-axis, it starts to, actually it doesn't really rotate it. That is because it starts rotating from a x-axis, and this original axis that I want to rotate is already on the x-axis, so trying to rotate a vector on the x-axis with the x-axis doesn't give you any values as an output, because what you're trying to do is, this is the rotational axis and this is the actual vector that I'm trying to rotate. So even if you try to rotate it, the point position doesn't really change. They have to be off the x-axis in order for this one to rotate. So that's kind of a reason why it didn't look like rotating. But if I change this order, like y, x, z, then you can start to use this x-axis, since you have first rotated the angle from the y-axis, then from this point you can now rotate this rotated vector with this x-axis. So you can do additional rotation here and then do the last rotation for the z. Alright. As you can see, using Euler angle is easy to read. It's human friendly to read, but on the other hand, it's a bit hard to control because you also need to consider how the rotational order have to be used. So most of the case, when you are doing the rotational transformation in VEX, I would suggest using a simple Quaternion function using an axis and the angle value instead of using Euler angle. What I would suggest is to use this Euler angle when you are retrieving the Euler angle from a node such as the transform. So there are some, let's say there are some setup it's being created using this transform to rotate an object, and you can actually refer to this angle by copying the parameter and paste it to the parameter of this angle to convert it into a Quaternion to do a rotation in Quaternion. So that's one way you would like to use Euler to Quaternion in a real practice. But most of the case, when you do a rotation by yourself, I would suggest using Quaternion, simple Quaternion function instead of Euler angles. Now that you have just converted the Euler values into Quaternion, there's also a other way around. You can also convert the Quaternion to an Euler as well. Now let's try to convert Quaternion to Euler. Now I am going to create another point wrangle connected to this one, and since in this wrangle I have already created the Quaternion value as an attribute named as Quat, I'm going to retrieve that first and change this to Euler, back to Euler. So Quaternion to Euler. And first of all, retrieve this Quaternion value, which is at p at Quat, and then there is a function to convert from Quaternion to Euler, which is called as Quaternion to Euler, and the first parameter is the Quaternion value, and the second parameter is again the order of the rotation. In this case, I'm going to choose X form X, Y, Z. Okay, and I'm going to update or store this value that I have retrieved as a degrees inside a vector attribute. Euler. Okay. Now let's go back to check if this was XYZ. Make sure this is XYZ, same as this one. Otherwise you get different kind of values. Now let's see, the angle currently is, let's say 30, 70, and 40. If you look to the Quaternion Euler, and they show up the geometry spreadsheet. It says 70, 30, 70, and 40, so it's exactly the same value. And sometimes you get a different kind of values, like if I change this Euler for the z to something like 200 and make the angle x for like 120, and if I go back to the Quaternion to Euler, now the value becomes a bit different. The x becomes minus 60, the y becomes minus 250, and the z becomes 20. Now let's check if this is still correct in terms of the final rotation. So let's remember this value, minus 60, minus 250, and 20. And also remember the angle right here, the current angle right here. So if you look from the top, if you look from the side. Okay. Now let's change this value to the one that we have shown. Let me check again. That was minus 60, 250, and 20. Minus 60, minus 250, and 20. Now as a result, it gives you exactly the same value. So even though the XYZ value seems different from the original one, the final output you get is the same one when you convert Quaternion to Eulers. So don't worry about it. This might be useful when you have a Quaternion rotational value and you just want to retrieve some of the axis related angle, either x, y, or z. But I myself don't use this as much as other functions. So just remember that there are functions like this if you need it. Now Quaternion is mostly used for rotation transformation, as I said, and compared to matrix, matrix can be used to do a transformation to rotation, translation, and scale. So it seems like the matrix can do a lot more than Quaternion and will be useful for most of the cases, but there are some benefits using Quaternion alongside of the matrices, that is the existing of a lerping function for the Quaternion, which means you can actually lerp between two Quaternion values to create a smooth rotational transformation from one angle to another angle. First of all, I'm going to create a add node to create a single point. And I'm going to create a point wrangle to create a line with a Quaternion value. So point wrangle, I'm going to call this Quaternion 1. Okay. And first of all, I'm going to create a normal attribute directly inside a point wrangle in y direction. So in this case you have, okay, I think I'm seeing some cache here. Go back, right. So I've just created this normal direction for this point. Now let's also create a angle as a parameter. Convert this into radians, and also create a axis, which I'm going to fix it as a 1, 0, 0, so x-axis. And let's create the Quaternion value named as quat using Quaternion. And the angle comes first, the axis comes next. Now I'm going to rotate this normal direction using QRotate. with quaternion and the normal direction. Okay, now let's see. First I'm going to promote the angle here, and let's set the range from 0 to 360 degrees. If I change this sliders, the normal angle or normal direction will rotate based on the x-axis by 360 degrees. Okay, now what I'm going to do now is to use this direction to add a new point from the center to somewhere around here to create a new point and connect those points to create the line. So int pt is equal to add point. Just going to directly use this normal value, which in this case should have a size of 1, which is defined here, and create the line using add trim and set as polyline type, and pt num is the current point number, which is on the center, this one, and the pt, which is the one that I have just created, which is somewhere around here, tip of the direction. Okay, as I do this, okay, now seems like I have a longer line. Okay, so I have just created the line like this, and if I rotate, it should rotate along with the vector, normal vector. Okay, now I am also going to set a detail attribute to this node named as quat1. So I'm going to store this quaternion that I've just used to rotate this line here. Right? Okay, 0 quat1. Quat1 for quat. Let me check. Okay, it's okay, I have to make it as semicolon. Alright, now let's check by going into the jump to spreadsheet to the detail attribute to check if I see this quaternion value being created. For the point, you have normal direction, right? Now, in order to use a Slerp, the smooth lerp between one angle to another angle, or one quaternion to another quaternion, I need another quaternion to do that, so I'm going to create another one by simply duplicating this node, and in this one I'm going to change the rotational axis. In this case, I'm going to set it as 0, 0, 1. Okay, and all the other one I am going to keep it as same. Just for the last detail attribute name, I'm going to name it as quat2. Okay, so that I have another line rotating in another direction. Right. Now what I want to do is to create a rotational lerp between the one that has been rotated with the quaternion 1 and one that has been rotated using quaternion 2. And by creating those lerp, I should be able to create some smooth rotational translations, rotate from this position to this position. So let's try to see how we can do that. I am now going to merge these two lines together and create another wrangle. In this case, I'm going to create a detail wrangle. First, create a attribute wrangle, and let's name this Slerp and change the points to detail. Alright, so that it runs once. Now first thing I would like to do is to get two quaternion value. One is quat1 and one is quat2, which is in the detail attribute. So quat1 and quat2. So vector for quat1 is p at quat1 vector for quad 2 is p at quad 2. Now, I have started rotating this line from a normal vector facing upward. So I'm also going to create this one as well. So I'm going to copy this one, copy this y directional vector, and let's name this as norm. Okay, instead of at n. Okay, now it's time to actually use the Slerp function. If you go to the geometry spreadsheet or the VEX functions page and search for Slerp, just this one, you can use it like this. So Slerp Q1, Q2 bias. So you have three parameters. One is Quaternion, another one's Quaternion as well, the second Quaternion, and the other one, for the third parameter, you type a flow value which is in between 0 to 1 to create a smooth interpolation from Q1 to Q2. Now actually it seems like there are a Slerp for matrix as well. So I guess you could also use, in Houdini you can use it for matrix as well. So maybe it might be okay using matrix instead of Quaternion as well. Okay, so let's go back to the Quaternion and let's go back to the Houdini and let's try to use this vector 4 quad 3. I'm going to create a new Quaternion values and use Slerp, and I would like to create a smooth translation or interpolation between quad 1 and quad 2 with some bias value which is between 0 to 1. I've just created a flow value which is in between 0 to 1. Now let's try to rotate this normal direction using this Quaternion that I've just created using Slerp by calculating the Slerp between these two Quaternions. Now you can do that by norm, saying norm equal to q rotate quad 3 norm. Okay, and let's also create a new point and lines to actually show where those lines are being drawn. So pt1 is equal to add point set 0, 0, 0, which is in the center, and int pt2 add point set, or I'll just use norm as it is, and connect those two points together using add prim 0 polyline pt1 and pt2. Right, now let's try to change this 0 value or t value from 0 to 1, and you can see the normal value or normal direction has been rotated from one angle to another angle. And if you look at it in 3D, this is actually not a straight a linear transformation, but you see some arc being drawn as well when it's rotate. That is because it contains the axis information as well for both quad 1 and quad 2. Both one has a different value for the axis, so that is creating this arc-like transition. Okay, and if you try to change the angle for the other one and try to change the angle for the other one as well, and change the t value again, we'll try to create a transition from one angle to another angle like this. with a minimum arc transition. Okay, so this is how it works. This is how Slerp works. And let me give you some practice how you can use this Slerp and a real practice as an example. Okay, so let's see. What I'm going to do is to create a simple animation, rotational animation for the box. From the first frame to the end frame, I'm going to try to rotate the box in different angle from with several steps. So from first, let's say from the first frame to 30 frames, I want to rotate the box from one angle to another angle, and from that I want to rotate it into another angle again with another random angle again, then do the same rotation in a range. Okay, so let me show you how you can do that. First I'm going to create a box, and in order to make it able to see the rotation clearly in what direction it is facing, I'm going to change the size of the X and Y and Z for this box. Okay, so to do that, I am going to set the X size to 0.2 and the Y size to 0.5 so that you have this kind of box geometry. Now, next thing I would like to do is to create some list of random angles that I would like to transition between. So to do that, I'm simply going to create something like for each number, and set the number to any value you want. I'm going to start by 5 and also use the transform node. And for the transform node, for all X, Y, and Z, I would like to set some random values for each iterations. And to do that, I need to get some different values from the iterations in order to use it for the random seed. So I'm going to retrieve the detail attribute for this for each count, which is called as iterations here, which changes from 0 to 4 and if you have total number of 5 iterations. So the first loop will give this value as 0, the second loop this value becomes 1, and so on. So in order to retrieve that, I need to write some expressions here. Detail for each count iteration 0, which will give you the iteration numbers here. And I would like to use this for a random seed value. So next I'm going to say random, and then give this iteration value, as well as I am going to multiply this or add with some prime numbers to make a difference, to make it look different from the other values. Maybe make it more complex, making as a float value. Okay, so I'm going to copy this one, paste it here, and I'm just going to change these and these as well. And currently the range for the random will create a value in between 0 to 1. So if you want to use this for the random rotation, I also need to multiply it by 360 degrees for everything. Now that I have enough random ranges for both, for all x, y, and z, rotational Euler angle. Next thing I would like to do is to get these Euler value here into an attribute, and later on I'm going to convert it into Quaternion using the functions that I showed you previously. So I am going to create a attribute wrangle, and let's set it as detail and connect it to this transform. And also I would like to access to the iteration attribute for this for each count, so I'm going to connect this to the second input as well. And let's say to detail attrib. Okay, what I would like to do is to first get these XYZ Euler angle. So I'm going to copy this channel here and then go back to the detail attribute. A detail attribute, then create the channel called rot Euler. CHB promote. And let's just paste what I have just copied from the transform node like this. And now next thing I'd like to do is to convert this into radians first. So radians, and convert this into Quaternion using Euler to Quaternion function. So Quaternion quat has to be vector 4. Quaternion quat, vector 4 quat is equal to Euler to Quaternion, and the first parameter was rotation in Euler, so rot Euler, and the second one is the order, which I can just say the same thing as this transform, which is in x, y, z. So x form x, y, z will do the job. Now I'm going to apply this into a detail attribute. Now I would like to also get the iteration number here and create a number of attributes based on the number of iterations. So the iteration value can be retrieved like access into a detail from the second input named as iteration, and use set detail attrib to a quat plus I2a, converting the integer value, the iteration value, into a string, and create the attribute name like together with the quat. So the first iteration's Quaternion value will be quat 1, quat 0. The next one will be quat 1, and the next one will be quat 2, and so on, with the value Quaternion. Right, now if we go out of the loop, if we check the geometry spreadsheet on the detail, you have quat 0, quat 1, quat 2, quat 3, and quat 4. Total 5 Quaternions in detail attribute. Now we can go back to this original box, and what I would like to do is to rotate this box based on those different Quaternion and based on those frame range one by one. So when it's the first range, it rotates from quad 0 to quad 1, and the second range rotates from quad 1 to quad 2, and so on, and loop the rotation using these information. Now using Slerp, right? So let's see how we could do that. We are going to use a point wrangle to control the points on the box. and connect this information which is included in the detail attribute to the second input, and let's name this rotation Slerp. Okay. Now, first of all, I need to know how many iterations we have right now. So let's create a integer at channel, just named as num, and copy this parameter and paste it right here with the link. Okay, now I'm going to first calculate the range of the frame based on this number. So what I'm going to do is to have the all the value here, which is the end frame, in this case 240, divided by this number, which is currently 5, so that I can calculate the step range for the rotation. So the end frame can be retrieved using $fend. So I'm going to divide it by a number, and I'm going to make sure that it's going to be float numbers just in case. Okay, now what I want to do now is to inside when you divide this frame into 5, and inside within those range, let's say that's between 1 to like 50, and between 1 to 50, when the frame goes from left to right, I also want to know the position of this point inside this range from 0 to 1 in a percentage or in the threshold as a threshold value. So I'm going to create the value in between 0 to 1 in what position in the range these current frames are in, and I'm going to name it as t. And to do that, first of all, I can use the current frame, which can be accessed as a at frame, and calculate the remains using modulus with the range that I have just calculated right here. And after everything has been calculated, after you have get the remain, you can then divide it with the range again to get the value in between 0 to 1. Alright. Now, now that I have the range from 0 to 1, I also would like to get the information in what range is the current frame is on. If the current frame is in somewhere around here, let's say that this is at the position 0. If it's on the second range, this is, let's say, the frame 1. If this is at the third range, then let's say the ID is 2, and so on. So based on the current frame's position, I would like to get in what number of range it is in. So you can get that. I'm going to name it as a current number. First of all, I can divide the frame by the range, and then calculate the floor so that you'll get the floor value. And just in case, when the frame goes to somewhere around here, this is only the place where you get value 5. But when you get value 5, you want to make it back to 0, because this is the only point where you get number 5, and after everything else you see different values from 0 to 4. So in order to prevent having number 5, value 5, I'm going to find calculate this with get the remains using the modulus with number, which in this case 5, so that if you get 5, then the index value will become 0, reset to 0. I also would like to get the next number next to the current number, which is pretty easy to calculate. You just need to add 1 to this current number, but there's also a chance that this value is going to be more than 5, so I'm also going to calculate the modulus by 5. in this case, number. Okay, now that I have enough information, let's try to calculate, or let's try to get the actual angle value for each of the frame range. Okay, so first of all, now that I have the current number 1 and the current number and the next number, which can be used as a iteration number as well. So I'm going to use these numbers as a guide to get to know which quaternion I would like to get. And currently I have quaternion from 0 to 4, so which matches with the number for the current number and the next number. So vector 4, the current quaternion, can be retrieved from the detail from the second input, quat plus I2A current number. Like this. And vector 4, next quat quaternion can be retrieved from the detail, quat I2A, and next num. Now that I have two quaternion values, I would like to calculate the Slerp, a Lerp value between these quaternion, and you can do that together with this t value, which is the value in between 0 to 1 in a specific range. In this case, a range between quaternion, current quat, and next quat. Okay, so vector 4, the last quaternion will be Slerp between quat 1 or current quat to next quat with t value. And now that I have a quaternion, we are ready to use this for the rotation. So at P is equal to Q rotate quat for quat at P. Okay, I think I have to say plus. All right, now I am seeing two boxes here. I'm not sure why. Let me check. Okay, I think it was a cache. So I think we are ready to do the rotational animation. So if I play it, see that there in total there is 5 different rotations being applied from one step to another. Okay, so if you change this to 3 or 2, maybe 3, in total you have 3 range, and using these 3 range to rotate from one step from one quaternion to another quaternion, and then to another quaternion, and so on. If you set it to 10, you have many steps to rotate from one to another quaternions, and just connects smoothly from end to the beginning. Okay, so this is one of the possibilities you can do with this Slerp functions, which I think is pretty useful. So yeah. Now hopefully you get the glimpse of what you can do with the quaternion. It's just about the rotation. Most of the things about quaternion is about rotation. So, and Houdini gives you a lot of useful VEX functions in order to calculate these rotations or do the rotational transformations in an easy manner. So I think you'll be able to use it right away. Even if you don't know about the back complex calculations of the vector for itself, it doesn't really matter. If you can use it, that's fine. in terms of designs. Okay, and I would like to show another functions which could be really useful as well, which is to orient one vector to another vector using Quaternion. And that is called as a dihedral, which I also use it a lot when doing some geometrical modifications. So let me show you how you can use it. Okay, so first of all, I am going to create like a random geometry, like let's say torus, and let's set the scale to 0.5. And also I'm going to create two lines as a vector to express as a vector. So create one line which, okay, facing upward is fine for this one, and for the other one I'm going to make it as random angle by changing it manually like this. So what I want to do is to use these two lines to calculate the angle goes from this line to this line. And to do that, there's just a function to do it, which is called as dihedral, and using that you can calculate a quaternion which rotates this first vector to this second vector, so that as a result you can use this geometry to rotate along this vector. So say this donut or torus geometry is facing upward, but you can change this to face it in this direction using this dihedral function. Okay, let's see how we can do that, which is pretty easy to use. I can create a point wrangle, connect those two lines. Okay, and I am going to retrieve the vector information out of these two lines. Let's give the ghost view here. Now the first vector, I'm going to name it as vector 1, and I will retrieve the from the second input P, which is the position, and the second point, because the line contains 2 points, and the second point will be the end point, which is the point that I need to calculate the direction. So this itself can be the direction. If you want to make sure, you can normalize this to make it as a uniform vector. And direction 2, I'm going to do the same process, but from this third input. Point to P1. Right. Now let's calculate the transformation from this vector to the second vector by using the function called dihedral, which can output the rotational quaternion transformation value. D1, D2. You just need to input two vector parameters in order to calculate the quaternion. Now you can just do the same thing like the other one. You can just use qRotate to rotate the point position with this quaternion, and as you can see, the torus now is facing towards the second line here. So if I rotate it, the torus will rotate along with these lines. Simple as that. Now this is pretty much it, but I'm just going to show you some other example in order to use this dihedral function in a bit more complex situations. Let's say I have this animated points running on top of the sphere, and on those sphere on the top of these points, I would like to get the normal direction on that surface and use that normal surface or normal direction to place some object with that direction. So I mean, you can easily do that using like copy to point node in Houdini, but let's try to do that. Let's try to do exactly the same things using a VEX coding to understand more about the transformation, right? So let's say I would like to move this rubber toy on top of a sphere. Okay. Let's make the size to be 1 to be, that should be okay. Now I'm also going to create a sphere, and let's set it to polygon and set the frequency to 10 so that it looks smooth. Now I'm also going to calculate the normal point normals using normal node with the point information. Right. Now I'm going to create the single point running on top of the circle like a spiral from top to bottom. And from that point position, I would also like to get the normal directional value out of this sphere geometry, and then use that normal direction to place this rubber toy using Dihedral function to orient. So let's see how we could do that. First, I'm going to create a single point like this, and then create a point wrangle to animate this point going upward and spiral using the trigonometry information that we used last time in the last session. Okay, so animate point. Hey, let's just make it pretty simple. First of all, I'm going to create an angle value in order for this point to go up and down. So, and using with this frame value as well. So let's say I'm going to start by calculating the pi multiplied by 2, which is 360 degrees, and multiply by frame values divided by fn. So as a result, you'll be able to get the value in between 0 to pi connected with this frame. So if the frame is 1, then you get the value close to 0. And if you are at 240, then you have value to multiply by pi. And if you use trigonometry, 2 pi and 0 gives you exactly the same value, right? For sine or cosine. Okay, now I am going to calculate the height of the point using a sine function together with the angle. So this will give you a value in between -1 to +1. It goes up and down, and since the radius of the sphere is also 1, so I'll just keep it as it is. Now I am also going to create a value for the radius for the point to animate spirally in XZ direction. Now if we think about how the point should transform, now the point is going up and down like this, right? At some point here, you want to get this radius right here, and what you only know right now is this h value and also the radius, the whole radius. Now the whole radius is equal to 1 currently, and h is already defined. So by having this r and h, you'll be able to get this small r as well. So currently this can also be estimated as r. So and this value here, let's say this is A, or maybe I can connect it, create a triangle like this, right? And this is the small r, this is the big R, and in this case h to r power is equal to big R 2. And if you want to get this r to power of 2, then r is equal to square root of r and h. Okay, so pretty straightforward. It's a Pythagoras theorem, so which can be done by square root 1.0 minus power of RH 2.0. Now, okay. Now that will be the radius. Now I can also create another angle value for the sorry. I have just calculated the radius by square root 1.0 minus power h2, like this. Now, if you want to create a spiral curve like this, then you need to know how many times you want to rotate. And 2 pi is the one rotation. So by multiplying 2 by integer value, you can estimate the number of rotations. So let's say float angle 2 is equal to pi multiplied by 2. And let's also use the same method here, so that it rotates based on the frame, and multiply by some integer value to define the number of rotations. If it's 1, it just rotates once. If it's 2, it rotates twice, and so on. Okay, now that I have two angles, it's time to, or height and those angle for the xz direction, and the xz directional value can be used to estimate the point's position on the circle by using cosine and sine together. So let's combine these together. So vector position set, so cosine sine will give you the circle position if you apply the same angle inside the cosine and sine. In this case, I'm going to create set angle 2 for both, and for the y I'm going to set h, and for the cosine and sine, which is on the xz plane, I'm going to multiply this by rad, this local radius value that I have just calculated previously. And as a result, by updating the current point position with this point, I should be able to rotate the point going around the circle or sphere like this. If you can see it, it's a bit hard to see. If you increase the number of rotations, you have more strong spiral movement. Now, it's good. In terms of the movement, looks good. Now what I want to do next is to get the normal direction at this point from this sphere. Okay, so let's create another point angle here, and after I get the normal direction, I would like to use this to create a quaternion value in order to rotate this base geometry, in this case a rubber toy. I'm gonna connect this rubber toy to the first input, and then the animated point to the second input, then this guide sphere geometry to the third input. Alright, so first thing I'd like to do is to get this point position from the second input. So vector pos point P0. And from this point, I'm going to get a normal direction from this geometry by sampling it, by getting the average sampled normalized vector using the point position as a guide. So to do that, there is just a function to do that. I'm gonna name the variable as nom, and by using a function called uv sample from the third input, and what we would like to get is the normal attribute, and use p as a guide position, and the position that I want to use is this position here. Now, as a result, you should be able to get, based on the point position, this animated point position, you should be able to get this smoothly sampled normal direction on that specific position. Now, after we get that, we could now calculate the orientation angle. Currently, let's say this rubber toy's base axis is y-axis, is the upper axis. So I want to create a rotational transformation, goes from the up vector to this normal vector that I've just created. So that can be done by using a dihedral from y vector to norm. And as always, we can use a qrotate to update the point position, or rotate the point position together with this Quaternion. Rotate. Now, let's also show up the sphere as well by merging these together. Now currently it is rotating based on the normal direction, but there is one problem, which is that the rubber toy is not placed on top of the point. Now that is because this qrotate only rotates the points from using the axis, but it is always from the center point of this world space. Okay, so whenever you have done the rotation from the center point, you have to move the actual point where you want to move the point, in this case from the center to the original point position, or the animated point position. To do that, you just need to add the position after you have rotated. Then it will stand on top of the sphere, set using this animated point as a base point for this geometry. Now it rotates around the sphere spirally. Alright, so this is one way you could use dihedral to calculate or to estimate the quaternion value from one vector to another vector. It's pretty useful in many cases, so remember how you can do this is pretty useful. Now this is it for today. I've shown you what quaternion is without explaining much of the theory, but what it actually is and what kind of functions are there for the quaternion in VEX in order to use for the rotational transformation. And quaternion is mostly used for the rotation. It is said that it is faster than using the matrix, so if you are just using the rotational transformation and you don't have any like translational scale transformation, then just using quaternion transformation might be a good idea. Anyway, I hope you get a glimpse of what it can do. with a quaternions, and it's not that hard to understand what it actually can do. So for the next topic, I would like to talk about the matrices, since the matrices is a big topic, the broad topic, and it's more complex than the quaternion, what it can do or what you can do with it. So I might going to split it into several sections, but I'm gonna start with the basics. Okay, so let's see you guys next sessions, and I'll end this session for today right here. And I have also started the Patreon page myself. If you have found these videos useful or helpful at some point, then it will be great if you could support me a little. I'll be really appreciated. Okay, thank you very much for watching, and bye bye.